Okay, continuing on today with the Laplace transform playlist, we have a really interesting topic. We're going to go over the Dirac delta function. So we have a graph of this thing over to the right, and it's pretty unusual. Now, this is going to be like our time axis, our t variable. And then what's going to happen is this function is going to be, and this is kind of related to the unit step function, where this function is going to be 0 everywhere, 0 forever. And then all of a sudden it spikes. And when it spikes, it has a width of 0. So it only spikes at this point A, and it goes all the way to infinity. But then immediately this drops back down, and then it's 0 forever. So this function is 0 everywhere except for at one point where it spikes to infinity. Now, of course, you can't draw a graph to infinity, but I just wanted to draw it this way just so that we can kind of get a visual for it. If you think of this like an electrical system or a mechanical system, it's modeling something that's like just stagnant, and then all of a sudden something happens with a lot of force. But now getting back to the topic of Laplace transforms, we're going to want to deal with this in a Laplace transform. We're going to actually want to take the Laplace transform of this. But looking at it, that's going to be a huge problem, right? Because Laplace transform is an integral. So the trouble with this when we deal with this in integral is it has 0 width, and 0 width usually means 0 area. But on the other hand, we're dealing with an infinite height. So it turns out there's not really any good way to deal with that in an integral. So this would be completely impossible, except for the fact that we have a few definitions that are going to help us out. Okay, so this first definition here tells us if we take the integral of the Dirac delta function from minus infinity to infinity, then that value is just going to be 1. So what this does is it actually defines this area that we have no way to calculate. It just defines it to be 1. And one thing to notice, the bounds don't actually have to be infinity and minus infinity, because if you had this, you could set this to some two values arbitrarily close to A. So basically what you could do for this is set your bounds to any B or C value, just as long as A is in that interval and not one of the endpoints. But what falls out of this first condition is this second integral, that if we take the integral of f of t times the Dirac delta function, we just get the function evaluated at this point A. So what's going on here is the Dirac delta function is defined to be 0 everywhere except for at A. So what it's going to do is it's going to zero out this whole integral at everywhere except for this point A. And then because this becomes 1, really all we're doing is just evaluating the function at that point. So now that we have these two properties here, we can get to looking at the Laplace transform of the Dirac delta function. Okay, so what we want to do is find the Laplace transform of f of t times the Dirac delta of t minus a. And for this, we're going to just go back and use our definition. So we'll integrate from 0 to infinity e minus st f of t times the Dirac delta. But now with this second property here, this is going to make this really easy, because this tells us we're just evaluating the function at the point A. So in our integral here, the function we're evaluating is not just the f of t, though, it's going to be this whole thing. So all we need to do is evaluate this at A, and then that's going to be our solution. So all we need to do is plug in. So we're going to have e minus sa, and this becomes f of a. And that's really all there is to it. That's going to be our formula for the Laplace transform of some function times the Dirac delta function. So we'll do a couple quick examples of this. So let's just look at the Laplace transform of just the Dirac delta function. And we'll just keep it generic, and we'll say we want to find Dirac delta of t minus a. And so this is just going to be e minus s times a. But then for our function, it's just a 1. So this is the whole formula for the Laplace transform of the Dirac delta function. But then let's just look at one with a function. So let's look at something else. Let's look at the Laplace transform of 4e minus 2t times Dirac delta of t minus 3, let's say. So then here, our a value is just going to be 3. So we have a equals 3, and we'll use that here. So we want e minus 3s, and then f of 3. So we just need to plug a 3 in here. So we'll have 4e to the minus 2 times 3. And then I can just simplify this and write this as 4, and then we can combine, we get the same base here. So I can write this as e minus 3s, and minus 2 times 3 is going to be minus 6, and that's going to be it. So as you can see, initially it seems kind of impossible, but this is actually probably like one of the easiest Laplace transforms we can do, because all we're doing is just plugging into the function we're just evaluating at the point A. So that's it. More Laplace transforms in the next video. Thanks everyone for watching. Have a good day.